Good afternoon and welcome to ECE 164. Today we're going to talk about common source amplifiers. And so if we think about ways that we can build amplifiers, and in particular I'm talking here about voltage amplifiers. And so what we're trying to build is something where we take a voltage in and we convert it to a voltage out. One way of doing this is using a device that we've already used or we've already learned, which is a voltage-controlled current source. So essentially, if we took this input voltage, delta V in, converted it into a current, delta I, we then just need to convert this current back into a voltage to get a voltage at the output. And we can do this through a linear element with a resistor. And so the idea here would be to convert the voltage with a transistor, a voltage-controlled current source, so a transistor operating in saturation, and then convert the resulting current back into a voltage through a resistor. It's a little bit indirect in how we're going to do this, but we can define the voltage gain essentially as the product of these two conversions. That is the product of the voltage-controlled current source, or the transconductance that's occurring here, multiplied by the resistance. And the product of this, again, gives us a unitless element where we're taking a voltage to a voltage. We'll talk later on in this course about other types of amplifiers where you take a current in and have a voltage output, or a voltage in and have a current output, or a current in and have a voltage output. So we'll go through all of the various different permutations, but to get us started, we're going to work with this very simple amplifier. Okay? And we're going to define the gain in this context as the ratio of the output voltage divided by the input voltage. Okay, and so or in our notation, we'll use V out divided by V in. All right, so if we look at this, the simplest way to construct an amplifier that looks like this is this type of construct here. So we have a resistor. One side we're going to tie to VDD for biasing reasons. The other side we're going to tie to the drain of the transistor. We're going to apply our input signal here at the gate, and we're going to take the output voltage V out here at the drain. We can write the current through this transistor ID. Assuming the device is in saturation, we can write that the current is equal to 1/2 mu NCox W over L times our input voltage Vi minus the threshold voltage squared. Okay. Now, if we look at a transfer function, a large signal transfer function, where I'm looking at the entire input voltage range from 0 all the way up to what would be VDD, and the output, again, V out from 0 to VDD, we see a handful of interesting regions here. Okay? And if I was to bias my input voltage with a DC voltage, a bias voltage, that was less than VT, the transistor is essentially off. When the transistor is off, ID is equal to 0, and so there's no current that drops across this resistor here, which means that V out is simply equal to VDD. Okay. Once I keep increasing V in above that point, at this point the transistor starts conducting current. We've entered saturation. Okay. We'll also call this region the active region of operation. So saturation and active for a MOSFET, they mean the same thing. Okay. And this is where we're trying to operate the device. Okay. We wanted to build a good voltage-controlled current source. A MOSFET in saturation acts like a good voltage-controlled current source. Okay? And so within this region, that is within VT and some point up here, which we'll calculate a little bit later, the device is in active region and it's acting as an amplifier in exactly the manner that we previously described, where we can write that the output voltage is simply equal to V out is equal to VDD minus the current, which we derive from this expression here, times this resistance. Okay? If we keep increasing the input voltage, if we keep increasing VI, and we go above this point right here, which again we're going to calculate, the device is going to enter triode. Okay? And so essentially what's happening in triode is that there's not enough voltage across the drain to source region to keep the transistor in saturation. Okay, so VDS, or the headroom as we call it across this device, is decreasing significantly. Okay? Now, coming back to what we wanted from this amplifier, we were trying to design an amplifier with gain. okay, with high voltage gain. And if I look at this, I'm essentially relating the input and the output. So the gain on this particular plot is the derivative. It's the slope. Okay. Now we can see that in cutoff, there's no gain. I can wiggle the input all I want, and the output doesn't change. Okay. There's zero gain there. In active region, I can see that the gain varies depending on where I bias the transistor along this curve. And that's what we need to talk quite a bit more about, is how do you bias this transistor to put it into saturation or into active region. Once I get into triode, you can see that the slope decreases significantly. What this means is that I have less gain in triode region. And so if you were to kind of look at this plot, if I wiggle Vn the same amount, if I'm in active region, I have a higher slope, which means that I get a higher gain, whereas in triode, the slope levels off and I end up getting less gain. Okay? So almost always when we're designing amplifiers, we will design them to operate in active region. So how do we do this biasing? This brings up an interesting question. We need some sort of battery, if you will, that puts the input voltage in the right place such that I can superimpose my signal, that is the point that I want to amplify, on top of this bias. And so we're going to talk a lot about how to generate these bias circuits in a few lectures and see many different ways that we can generate this. For right now, I'm just going to artificially add a bias voltage source. Okay? And we'll see later on that adding a voltage source is not a very good or robust way to bias this circuit, but it's sufficiently simple that it'll work for right now. Okay? Then we have our overdrive voltage, where our overdrive voltage is the difference between this voltage, the input bias, and the threshold voltage of this transistor. Okay? And this is essentially what's going to set where on this curve we superimpose our AC or our small signal response. Okay? And so this bias point, this is really where we're trying to set the operating point of the transistor. And anytime we're talking about large signal biasing, DC biasing, we're talking about no AC signals. Okay? So whenever I do that, I'm going to take away my lowercase vi, my lowercase id, lowercase vo, and only look at the DC operating point. And so the overdrive voltage here is VGS with minus VT with no input signal applied. Now, as we've talked about in lecture 2, all of these signals can be decomposed into their bias point, that is their DC point, as well as their AC value that's superimposed on top of that. Okay. All right, so now let's take this to the next step and let's derive a relationship between the input and the output voltages. Okay? But rather than just look at the small signal voltages, I'm going to include the DC bias, and I'm explicitly going to break this out. Okay? And so what I mean is that at the input, I'm putting that we have an overdrive voltage plus our AC voltage, and similarly at the output, I will have a DC voltage plus a small signal voltage. And so if I write this expression, I can write that the DC, or the instantaneous output voltage, is equal to VDD minus 1/2 mu NCox W over L times VOV, the operating point, plus my small signal component, okay, VI, times the resistance. Okay. If I take away the DC operating point, that is, I look at only the small signal response, I can massage this expression. Okay? And I can calculate what V out is by moving VOV back over here. And so essentially what I'm doing is I'm first calculating the DC operating point. And once I've taken the DC operating point, now I'm looking at only the small signal response of the circuit. Okay? So only the effect change due to V out after we've already found the operating point. And so what I can do is I can continue to simplify this circuit, and I eventually get that the small signal V out is simply equal to minus 2 times ID divided by VOV. This is due to my DC operating point. times the resistance times the input voltage. And then there's the second order term. That is, I have this VI divided by 2 times VOV term. Now, unfortunately, this is a nonlinear relationship. It's nonlinear because I have VI squared on this right side. So I have a first order linear term that has only VI, but I also have this squared VI term. Now, it turns out that really nobody likes nonlinear equations. But in particular, circuit designers hate nonlinear equations. Okay? So we really need a simpler model or a simpler way to work with this. Now it turns out that luckily, a first order linear approximation is sufficient for most circuits. Okay? Not all circuits. There are a handful of circuits that transition between different operating points or that have very large signal behavior. But I would say for 90%, and I'm completely making up this number, this particular framework that we're going to develop is sufficient. All right, so as I said, this is that second order distortion term, and it really occurs because we have VI times VI here. So if I look at this expression, it tells me something rather interesting. Okay? In particular, if I wanted to minimize the second order coefficient of VI, what this means is that if I kept this denominator small, and when I say small, I really mean small relative to VI, I could approximate away this term relative to 1. Okay? And so that's what we're going to do. Let's pretend, or let's assume, that we have the input small signal voltage is much, much less than 2 times our overdrive voltage. And when I say much, much less than, I mean a factor of 10. Okay? If I have this being a factor of 10, then the output voltage, Vout, is approximately equal to minus 2ID divided by VOV times R times VI. Okay? So this is nice. These are DC bias points. This is set by the circuit, and this is our input voltage. And so now we have a linear relationship between the input voltage and the output voltage. You can also get at the same result in a slightly different manner. You can essentially use calculus to say that if you were to take the derivative of the output with respect to the input, given the condition that the input, the large signal instantaneous voltage is only the DC bias point. And so what that essentially is saying is that we're making the input voltage infinitely small. You would simply take the derivative of the expression, and we would get this same term, that the gain was equal to minus 2ID divided by VOV times R. Which is exactly the expression that we got here using our alternative route. We could similarly plug in the expression for ID and simplify this expression. Okay? We'd get that it was negative, meaning that we're getting a phase change in the signal. It's 180 degrees out of phase with the input, times mu NCox, W over L, VOV times R. Okay? And again, we're going to call this the gain. This is our small signal voltage gain. Our large signal voltage gain we would get from that transfer curve that we looked at earlier. Here, this is a small signal voltage gain that's linear, provided that we don't disturb the bias point. And by not disturbing the bias point, we have to maintain this condition, that VI is much, much less than 2 times the overdrive voltage. All right, so if we look at this graphically, coming back to this large signal transfer curve that I showed you earlier, here's VT. Below VT, we have no gain. Once we position our bias point VOV above VT, this is our DC operating point. The slope of this transfer curve at this point is our gain. That's the DVO dVi, or Vout divided by Vn, or our voltage gain that we were calculating. Okay, this is the small signal voltage gain of our amplifier. Now it turns out that this framework, we don't have to do this for every single circuit that we design. We can use this linearized circuit model for the transistor and plug it into arbitrary circuits. Okay? And so really what we're doing is we're taking an ID versus VGS curve that is this shape here, this nonlinear shape. We're linearizing the circuit by picking one particular operating point, and around that operating point we are drawing a linear extrapolation. Okay? And so essentially what we're doing is we're turning this into a transconductance, a linear transconductance. Okay? And so in order to take this nonlinear transistor and do this transformation into a small signal model or a linear model, we need two conditions. One, we need VDS to be greater than VOV. This is simply saying that the device is in saturation and that it's not in triode. Okay? And we need VGS, that is our small signal input voltage, to be much, much less than 2 VOV. This is that same approximation that we came up with earlier, and it simply is saying that we're not disturbing the bias point significantly. Given these conditions, we can create a linear small signal model of this otherwise nonlinear device. Okay? The parameter that we use this is called the transconductance. This is the GM. Okay? The GM is found by differentiating the large signal IV characteristic of the transistor around its operating point. Okay? And so if we take this ID expression in saturation and we calculate its derivative with respect to VGS, we get this expression that we more or less saw in our previous derivation, where we said that the transconductance is 2ID divided by VOV. Okay. Similarly, we can plug in ID and we can get expressions with respect to VGS and with VT, or you can also find an expression that has a square root term if you just manipulate this expression. Okay? But let's spend just 1 second and think about what this means. If I was to bias a transistor with more current, that means that I get higher transconductance. Okay? Similarly, if I bias the transistor with very low overdrive voltage, this also tends to maximize its transconductance. Okay? And so we'll see these two kind of paradigms play out as we go through a few examples and look carefully at designing circuits with this. All right, so how would we use this type of model? We would first analyze the circuit that's shown here on the left that includes our DC biasing. We're going to use the large signal IV expression in order to calculate the operating point. And when I'm talking about the operating point of any circuit, I really mean all of the branch currents and all of the node voltages. Okay? Once I have the operating point, then I can use all of the operating points in order to calculate the small signal parameters. Okay, so in this particular case, we can calculate the transconductance of this device. Once I have all of this, then I can redraw the small signal equivalent circuit where I remove all of the DC bias. Okay, and so removing the DC bias in this case means that any DC voltage essentially has 0 volts. So this goes to 0, and I'm left with just my small signal source. Similarly, VDD also goes to 0. Okay? And so I have my very, very simple small signal circuit that's shown here, and I can do all of the other calculations that we're going to do for the next several weeks where we talk about gain, bandwidth, any other small signal parameters. So let's do an example. Let's take this same circuit that we've been talking about for a while, and I'm going to give you a few technology parameters and inputs. So the input DC voltage is 550 millivolts. We've sized the transistor to have an aspect ratio of 20/1 microns. We have a 5 kilo ohm resistance, and we're operating with a 1.8 volt supply voltage. The transistor has a transconductance parameter of 450 microamps per volt squared, and we have a threshold voltage of 400 millivolts. So the first thing that we need to do is we want to calculate the operating point. We want to calculate ID, Vout, GM, as well as the small signal gain of the circuit. All right, so the first thing is that we'll write the ID expression Okay, we directly know VGS in this case, and the source is grounded, so this will immediately give us the drain current. So taking these parameters and simply plugging them into our expression of ID is equal to 1/2 mu n Cox W over L times VGS minus VT squared. Okay. I will get a current that is 101 microamps. Now, I'm lazy, and I'm going to approximate this as about 100 microamps, okay? Just to keep the math simple for slides. So if this current is approximately 100 microamps, that means that there's 100 microamps times 5 kiloohms voltage drop across this resistor, okay? Which means that the output voltage is equal to VDD, or 1.8, minus 5K times 100 microamps. Okay? And so this puts the output voltage at 1.3 volts. Okay? Now, implicit when I chose this expression up here, this ID expression, I assumed that the transistor was in saturation. And anytime I'm doing DC biasing, I always have to pick an assumed operating region for any active device. Okay? We'll get really good at looking at circuits and kind of reasoning out what region of operation we think they should be in, just based on kind of pattern matching and familiarity with circuits. But always starting off with a device, an active device, and assuming that it's in saturation is usually a good bet. Okay? But we need to check this. And so now when we look at this, we need to make sure that VDS is greater than VOV. Okay? And so in this case, VDS is simply equal to Vout, which is equal to 1.3 volts. And so that's good. VGS minus VT is equal to VI minus VT. So VOV is 150 millivolts. So this device is in saturation. So now I can compute the small signal parameters of this device, namely the GM and the small signal voltage gain. Okay? And so GM is equal to 2ID divided by VOV, 2 times 100 microamps divided by 150 millivolts. I get 1.3 millisiemens. The voltage gain is simply minus GM times R. So over here, this transconductor takes GM times VGS, converts this into a current, and this current is reflected back into a voltage through this resistor, exactly like our block diagram that we started out on slide 2. And so the voltage gain is simply minus GM times R, which is minus 6.5 volts per volt. All right, so this circuit was really easy. And we probably couldn't have made many mistakes even if we tried. However, what we're going to see is that our circuits are going to get much more complicated as we go out through this class. And we want to be able to always do hand calculations on circuits. Okay? Simply throwing things into a circuit simulator is not the only way to deal with circuit design. We should use the simulator as a way of checking our hand calculations. Okay, and so you'll see this many times on the homework throughout this quarter. We will first do hand calculations, then we will go simulate the circuit, and we will try to resolve the discrepancies. Sometimes in our hand calculations, we'll ignore things like channel length modulation or the body effect under the presumption that they don't have a big effect on the circuit's performance. Whereas the simulator will take into account all of these effects and simulate everything. Okay? And so in this way, it's not really that one replaces the other. They're both important. We need to use the hand calculations with simplifications and assumptions in order to develop intuitive analysis and intuitive methods in order to be able to fix and change and manipulate the circuit, whereas the circuit simulator is nothing more than crunching the numbers. Okay? And so, you know, I count this as double bookkeeping in some sense that we're doing this twice, once by hand and once through the simulator, but it's important to really understand the circuit. Okay? And so what I want to do is I want to take this very simple circuit that we just did, and I'm going to duplicate the results using cadence. So here I've created a schematic. I've used ground, and this is a very important point in cadence. It always needs a reference point. Okay, we always talk about ground being our reference point. Cadence needs to know what reference point you're talking about. So we always need to have a ground tag. From this ground tag, I've applied a DC voltage that I'm going to use as my supply voltage. And so I've set this to be 1.8 volts. I've connected a resistor right here, R0, that's 5 kilo ohms. I'm applying an input voltage source, okay, with an amplitude of V amp that I'm setting as a parameter, frequency of F1, and a voltage, a DC voltage of VBN. Okay, and you can see these three, I'm using them as parameters, so they don't show up on the schematic, but in ADE, I can set their parameters. The reason why I like to do parameters for a lot of these circuits is I can sweep them. I can sweep parameters very easily to look at various different aspects of the circuit or to do parameterized sweeps. Lastly, I have the transistor, okay, where I've set its width again to a parameter W1. I've set the length to 1 micron. Number of fingers I've set to 1. We'll talk about fingering later on. For right now, just put 1. And multiplicity or number of transistors M, I've also put at 1. Okay. And I've connected the source of this to ground and the drain up here, and I've labeled this net out. Okay. And then lastly, I've put what's called a no-con. This no-con, this symbol is available in the basic library. And no-con, essentially what it does is it gets rid of a warning in Cadence when you try to save a schematic that has a wire dangling out here. It won't give us that warning anymore. So this symbol again, no-con, N-O-C-O-N-N, it's in the basic library. All of these other components, this one I chose from the analog library, analog library, analog library, and this one from our PDK. Okay. I've also put net names on this in order to make things a little bit more readable. Otherwise, Cadence will randomly pick a net name for you, and it usually is a very long, convoluted name. All right, so the very first thing that I'm doing is I'm sweeping the DC operating point. Okay, and so what I've done here is I've run a DC sweep where I've swept VBN, or this bias voltage, from 0 all the way up to 1.8, and I'm plotting the output voltage. Okay. And so this should look very familiar to that cartoony plot that I showed earlier. We can see that the device here is in cutoff, transitions into active. This is where I'd like to bias the device. And then down here, it's coming out of active or saturation, and we're entering triode. Okay. So this is exactly what we'd expect. It matches our hand analysis. In addition to that, we can also look at the DC operating point. Okay, and so this DC operating point, I can annotate it on the schematic, or I can print the DC operating point of this transistor. Okay, and so this is a good thing to learn how to do. Sometimes it takes a little bit to read and understand what all of these different parameters mean, and so I'll just spend 1 second and kind of explain what's going on here. So the VBS, this is the body to source voltage. VDB, this is the drain to body. VDS, drain to source. VDSat, this is the saturation voltage for velocity saturation. VGB is the gate to body. VGD is the gate to drain. VGS, VTH, this is the threshold voltage. GM, that's our transconductance. Region, this specifies the region of operation for the device. You can look up what each of the regions are. 0 is cutoff, 1 is triode, 2 is saturation, and 3 is subthreshold. So we're operating in saturation. And V early, this is the early effect voltage, is 7.27 volts. Okay. So all of this really tells us a lot of detailed information about this transistor. In addition, I've also annotated onto the schematic the current of each of these sources, as well as the DC node voltages. Okay. All right, so this transistor looks good. It does have a slightly different threshold voltage than we assumed in our calculation. So we assumed that the threshold voltage was 400 millivolts. In fact, when the simulator did all of the calculations, it came up with a threshold voltage of 392 millivolts, which is why our transconductance is slightly off of what we calculated by hand. All right, so next I've run a transient simulation. Okay, and so this transient simulation is applying a sinusoidal source at the input. Okay, and so you can see my DC offset here along with my AC input. And I'm running this entire simulation for 20 milliseconds. Okay? And you can see the output is out of phase, so 180 degrees out of phase with my input. That's where the inversion comes in from our common source amplifier. But you can see that my amplifier has gain. Okay? The output voltage is larger than my input voltage. Okay, so next I can run an AC simulation. And so an AC simulation, what I'm doing is I'm sweeping the frequency of the source and I'm plotting the voltage gain along with the phase. Okay, and so this is the gain in decibels and the output phase and frequency. If I look here, I can see that I have about 13.56 dB of voltage gain. Okay? And up to fairly high frequency, I have a flat gain response. And then the gain starts to roll off a little bit due to the frequency response of the circuit, which we'll talk about in a couple of lectures. Okay? Importantly, we have an inversion. So we have 180 degrees phase shift. This is again due to the input signal and the output signal being 180 degrees out of phase. All right, so if I look at this and I take 13.5 dB and I back it out into volts, I see that I only have 4.76 volts per volt. Okay, so we designed this circuit in our hand analysis to have a gain of 6.5. So why do we only have a gain of 4.76? Well, it turns out that there's channel length modulation that we did not account for in our hand calculations. Okay, and so what we're going to do is we're going to go back and we'll fix this in order to deal with this channel length modulation. We assumed that the load resistance was R, not R parallel R naught. The other interesting thing is that if I was to take this out of decibels and put it back into just volts, if you look here, it seems like I could have an output voltage, the magnitude of V out, that was 4.79 volts. Okay? How could this possibly be, given that I have a supply voltage in my simulation right here of 1.8 volts? So somehow in my AC simulation, this voltage can go up to 4.7 volts. Or at least that's what the simulation is telling me. However, if I was to try to run a transient simulation with a very large input would show me that the voltage can only go up to 1.8. Okay? And so this is really important that we understand what's going on in the simulation. When I do an AC simulation like this, okay, the simulator does the same things that we did when we were analyzing the circuit. It first finds the DC operating point. Okay? It does that with a DC simulation. Then it linearizes the circuit in the exact same way that we did. Okay? And when we linearize any circuit, we lose all notion of the supply voltage and clipping that would otherwise come into play. Okay? And so be very, very careful when you're trying to understand AC simulation results. Okay? Transient simulations never lie. Okay? Transient, it takes into account all large signal behavior of the entire device. And this is why transient simulations often take much longer and are computationally more difficult than simple AC simulations. But you can see that the transient simulation here correctly captures the clipping behavior that would happen. That is that the transistor could not actually get that circuit to go above 1.8 volts. It clips it off right at about 1.8 volts. And we end up with what's going to be called very nasty distortion. So again, just to reemphasize this, whenever we do an AC simulation, the circuit transfer function is going to be linear. Okay? It extends from minus infinity to plus infinity. If I put in 1,000 volts, it will have 1,000 volts times the gain. Okay? It doesn't take into account things like finite voltage range, signal clipping. These notions don't exist in any small signal model. Okay? The other thing to remember is that when we're doing an AC simulation, we can put the input amplitude as any number. Again, because it's a linear circuit at this point, there's no notion of pushing the transistor out of saturation. I typically use 1 volt. Okay? I use 1 volt because then I can simply probe the output voltage and I've already measured the gain. If you use a different number than 1 volt, you have to divide the output voltage divided by the input amplitude that you used. All right, so the operating point for the transistor the example that we just did was relatively straightforward. Okay? We essentially did a couple of steps. One, we assumed a region of operation for each device. In this case, we assumed that the transistor was operating in saturation. Second, we computed the drain current via a simple closed form expression. Okay, so that was the ID expression that we used. There is no AC signals present when we are doing the DC operating point calculation. Third, we have to go back and we have to check that our result is consistent with our assumption. That is, given that I made this assumption, did the result that I got when I computed the operating point match this assumption? If it doesn't, then I have to pick a different region of operation and repeat this. I.e., if the transistor was actually in triode, I would get that the VDS essentially would not match the condition that I need for it to be in saturation. The operating point is typically the most difficult thing for circuit simulators to do. When we take all of the nonlinear IV characteristics and the multitude of regions of operation that these transistors can be in, finding the DC operating point of very large circuits is often the most difficult thing. Okay? And this is usually where the simulator gets quite hung up. There are some tricks that we can play, and I'll teach you them as we get later on throughout this course. But just think about the problem that the simulator has here. It has a whole bunch of different transistors with all highly coupled nonlinear expressions, and it needs to try to figure out the one particular region of operation. Okay? And so to give you just a slight feel for this, I'm going to do a slightly more complicated, still not complicated, but slightly more complicated circuit. And we're also going to look at how SPICE would handle this calculation. All right, so somewhat familiar circuit. I've added another resistance in the source. Okay, so I've added drain resistance. I have a MOSFET, an NMOS, size W over L, and I've added a source impedance down here, R1. Okay, we're still taking the output at the drain and applying the input at the gate. And so I'm giving some parameters. The input is 2 volts, W over L is still 20 over 1, 5 kiloohms, and I have 25 kiloohms of resistance for R1, a supply voltage of 5 volts. I'm still using mu NC aux as 50 microamps per volt squared, and VT is 0.5 volts. Okay? And so what we want to do is we want to calculate the drain current. This particular circuit, by the way, it's called a common source amplifier, but it has source degeneration. Okay? We're only going to look at the DC operating point of this. You'll get to look at the small signal transfer function in the homework. Okay? The circuit also has a form of feedback that we'll talk about later on in the course. It has a form of feedback called series feedback. All right, so first step, we're going to assume that the device is on and that it's in saturation. And so I use my ID expression. Okay? Now, unfortunately, previously we directly knew VGS. VGS was easy to calculate in the previous example because the source was grounded and I applied a DC voltage right at the gate. Okay? Unfortunately here, VGS is equal to VI minus the drain current times R1. Okay? And so in this way, the input and the output are highly coupled. And so I need to solve this expression. I need to find the roots of this. So I need to find the two roots that come out of this ID expression. Okay? And so if I go through a little bit of math and I plug in all of the numbers, I'll essentially find that this particular circuit has two currents. Okay, and so if I was to plug in those numbers, I would get that ID1 was 500 microamps and ID2 was 180 microamps. Okay? Now this circuit can't actually have two operating points. One of these has to be incorrect, and so it's up to us to figure out which of the two currents is incorrect. Okay? And so if I was to compute VGS, where VGS is equal to VI minus ID times R1, for these two different currents, I would get that VGS is equal either minus 0.5 volts or 1.1 volts. It can't be minus 0.5 volts, because if it was minus 0.5 volts, the device would be in cutoff. Okay? So I know that this particular case of ID is equal to 500 microamps is not correct. Okay? So ID has to be 180 microamps, which gives me a VGS of 1.1 volts. Okay, so now let's go back and let's check our assumption that the device is in saturation. And so I compute VDS. VDS in this case is simply VDD minus the voltage drop across this resistor minus the voltage drop across this resistor. Okay, so this is ID times R1, and the second one is ID times R2. In this case, VDS would be minus 400 millivolts. And so this particular circuit cannot have VDS of minus 400 millivolts. If it has a VDS of minus 400 millivolts, that means that the device is not in saturation. And so what this means is that I get to get really, really annoyed, and we have to redo all of these calculations, now assuming the device is in triode. So how would SPICE do this? SPICE essentially is going to do the same thing that we did, except for it handles much, much, much larger circuits. Okay, this one transistor circuit is very easy. Okay? So SPICE is not a tool that symbolically just solves these expressions and plugs them in. It really is nothing more than a matrix solver. It's a numerical method applied to a linear version of this circuit in order to find the operating point. Okay? And so in order to understand this a little bit better, let's look at how SPICE treats transistors. Okay? So SPICE takes this transistor and it applies these same exact expressions, these nonlinear expressions. However, it does a little bit of linearization or conditioning on the circuit. Okay? And one of the things that it does in order to make sure that the circuit is factorable or has a solution is it adds conductances. Okay? And what I mean is it adds impedance from every node to every other node. Okay, so even though you, as the designer, did not explicitly draw these resistors, SPICE will add these resistors in order to make sure that it can solve the matrix that exists when it computes the entire nodal matrix of the circuit. This particular parameter, it often adds the default value is it's controlled by a parameter called Gmin. Gmin sets the minimum conductance, where it essentially adds a 1 gigaohm resistance between any node in the circuit and any other node. And what this does is it provides a conductance path, albeit very, very small, between those nodes. Okay? So normally, this is not a problem. Okay? I don't really care if I have a 1 gigaohm impedance between multiple nodes in my circuit. However, there are times when you are designing circuits that are either very, very low power, they have impedances themselves that are comparable to this, in which case we need to know to go in and change this parameter and increase the tolerance. Okay? What's the impact of doing this? Well, it essentially makes the simulation harder. SPICE has to work harder in order to find the operating point because it can't condition the matrix quite as effectively. All right, so After this, what does it do? It essentially does what we do. It really just solves KCL and KVL. It tries to sum all of the currents entering and leaving a node, making them to 0, and voltages around a loop, making it equal to 0. In reality, it's actually quite a bit more complicated than this because it has to do iterative matrix solving techniques. It doesn't try to symbolically solve these expressions. It uses matrices and one of these 4 matrix solving techniques in order to come up with a numerical approximation of the circuit. So this can lead to what are called convergence issues. So convergence issues are essentially when it cannot find an operating point. Okay? And it can't find an operating point is really frustrating because it's difficult to debug these types of issues. It turns out that it's not so much of a problem with modern simulators. Today's tools can really handle very, very, very large circuits, even 10,000 or 100,000 devices. The more common region for non-convergence or for circuits that are hard to figure out an operating point is a bad netlist or an improper settings. Okay? And so, just to give you an example of this, if you were to decrease G min and put it at an arbitrarily small value, essentially that would make it very difficult for the simulator to be able to find any operating point. Okay? Another common mistake is that not putting a ground symbol. If you don't have a ground symbol, it can often get into this kind of situation where it can't find an operating point. So chances are that if you're getting a convergence error, it's not actually the tool. It's simply that you've made a mistake in your circuit. Okay. All right, so what kind of analysis can SPICE do? Well, a DC analysis or an operating point analysis, we've talked quite a bit about this. This particular technique finds the operating point of a circuit. That is, it finds all the node voltages, branch currents, and region of operation for every active device. Okay. When it does this, it does the same types of things that we do. It shorts out inductors, it opens capacitors. Importantly, it always has to do this before it can run an AC simulation. It needs to know where to linearize the circuit. Okay? It's also always done before a transient simulation because it needs to know the initial condition for the simulation. Okay? Transient condition, it computes the transient voltage over user-specified time. So this is to simulate what we'd actually measure in the lab if we were hooking up an oscilloscope. Okay? And the initial conditions are determined by either a DC operating point or they're overridden or defined by the user. Okay? And so what this means is that if there's a capacitor or an inductor or any other energy storage element in your circuit, unless you tell it, SPICE will just use a DC operating point in order to figure it out. We can use commands like node set in order to tell it what that voltage should be or current should be rather than to use the operating point. And then lastly, we can use AC analysis where we're going to look at the linearized response due to a small signal input. Okay? So there are other types of analysis that SPICE supports. These are the main 3 that we will use in this course, and these are probably the workhorse that you will use in general throughout your career. Thank you.